Thank you for choosing Jaga's online CPD course outlining the theory behind the design and specification of trench climate convectors, covering heating, cooling and ventilation. Before we start the presentation, here's a short introduction to Jaga.
How do we make sure we'll be treating the climate much better in 10 years and beyond? This question is where our work begins today, every day. We are Jaga. We develop products that contribute to a healthier and more pleasant indoor climate. We do that with the least possible impact on the environment. Contributing to a sustainable future is no longer an option, it's an obligation for all of us. The industry should offer nothing but responsible choices. At Jaga, this is a mission we feel very strongly about. For more than 50 years, we've been creating sustainable cooling, ventilation and heating solutions. Our products are lighter, smaller and quieter than traditional systems. They require less material and they're a lot more energy efficient. Our products last for at least 30 years and are fully recyclable. Good for people, good for the environment. That is why we call ourselves climate designers.
This course will cover the types of trench convectors available and different applications. We'll take you through the design and selection process for heating and cooling, and we'll touch on ventilation. We'll also take you through the options available to add value to your design in terms of aesthetics and engineering. The learning objective is simply to give you confidence in the design and specification of trench climate convectors. Trench climate convectors can be integrated into any type of building, but those with large glazed facades are most likely to require this type of product due to the limited wall space. Buildings like this are an increasingly popular choice for architects and homeowners, providing clean architectural lines and natural daylight. For mechanical engineers, they pose a challenge in terms of the associated solar heat gain, heat loss, and the possibility of cold drafts. This course will cover some of the solutions to overcome these issues. Another increasing area of activity is residential buildings, particularly apartments within high-rise city centre tower blocks. Consumer expectations are high, and there is an increasing demand for thermal comfort throughout the year, comfortable heating in the winter, and refreshing cooling through the summer. Wall space is generally precious within these buildings, making compact trench convectors an optimum solution. Other applications include educational environments, healthcare settings, places of worship. The list is endless. There are 3 types of trench climate convectors available to suit different design aspirations: natural convection, fan-assisted, and forced draft. If you only need heating, then natural convection is the simplest solution. This means there's no fan, so no forced air movement and no noise. It purely relies on the hot water warming the air around the heat exchanger and creating natural air movement. An alternative for a heating-only application is fan-assisted convection. These units operate in the same way as their natural convection counterparts, but with the addition of low-noise fan units to provide increased performance when needed. The third type of trench climate convector is forced draft. Forced draft units deliver high performance, low noise, heating and cooling from one single unit. They can only operate with the fan running and are capable of providing thermal comfort in living and occupied spaces throughout the year. The heat exchanger, sometimes referred to as the coil or element, is fitted inside the trench unit. It transfers the thermal energy of the water, whether that be hot or cold, to the air and the occupied space. Heat exchangers are available as either a 2-pipe or 4-pipe configuration. 2-pipe heat exchangers consist of one coil for both heating and cooling circuits, with one flow and one return water connection. This arrangement can generally provide higher performance than the 4-pipe alternative. A 4-pipe consists of 2 coils, one heating and one cooling, with independent flow and return connections. This is generally the preferred option for commercial large-scale buildings that could have demand for cooling and heating simultaneously in different parts of the building. Ventilation is a key consideration in any building design, and this can be incorporated into trench climate convectors via a connection to bring fresh air into the space. Trench climate convectors are designed to be integrated into the floor, so the only part you can see is the grille. A wide range of grilles are available that offer hard-wearing, practical and decorative solutions to suit various interior designs. The choice of grille may have an effect on the heating or cooling performance, and this will be covered later. Here is a selection of grilles available. There are many benefits to installing trench climate convectors. One unit can provide heating, cooling and ventilation, offering thermal comfort throughout the year. They help maximize the lettable or living space. They're architecturally pleasing, as they're tailored to fit building contours and aesthetics. They're designed to be compact and discreet. They're suitable for low water temperature systems, such as heat pumps. They offer powerful heating and cooling performance for full or partial load. Natural convection, fan-assisted, or forced draft options are available to suit all requirements. They can be speed controllable, energy efficient, and ultra-low noise. The casing can be used to lay or install other services and equipment, and they provide a low-maintenance solution. So now let's talk about design. When starting the design process, we must always consider the space and design objectives. We'll go through an example of a commercial space, with 2 fully glazed facades and 2 internal walls. The engineer will calculate the heating load requirement for the space. In this instance, we have calculated a requirement of 13 kilowatts. The design condition is 75-65-20. This means the flow temperature into the unit is 75 degrees, the return temperature out is 65 degrees, and the room temperature is 20 degrees. In order to make a product selection, we need to establish what available space we have. This would typically be the available width between the window frames. In the example, we have a total of 4 sections at 3.75 meters and 3 sections at 1.5 meters, giving us a total of 19.5 meters. From this, we can then calculate the heating requirement per meter by dividing the heat loss of 13 kilowatts by the overall length of 19.5 meters to give us 666 watts per meter. Generally speaking, glazing loses more heat than any other building material. Therefore, the glazed facade is the highest source of heat loss. If we have a separate main heat source for the space, our trench climate convectors only need to provide sufficient heating to overcome the losses through the glazing. Start by calculating the heat loss of the glazed area and use this figure as a minimum requirement. It's fine to go for a bigger unit if preferred, as this will complement the main heating source. For glazed facades over 5 meters high, it is recommended that fan-assisted or forced draft trench climate convectors are specified. In this example, we have calculated that the heat loss of the glazing is 3.3 kilowatts. Again, we divide this by 19.5 meters, and this will give you a heating requirement of 169 watts per meter. When considering available space for trench climate convectors, please be aware that there is a difference between the active length and the inactive length of the unit. The active length is effectively the length of the heat exchanger within the trench. The inactive length incorporates valves, pipework, and controls. Selection is nearly always based on watts per active meter. Now that we've established the available length, the next step is to consider the available depth. We do this to determine the height available for the trench unit. As per these examples, the depth can vary significantly from project to project and can certainly vary within one single building. Generally, the available depth in commercial buildings is greater than that of residential buildings, where the trench is typically set in the concrete floor. Restrictions on the width of the trench will also be a consideration in terms of aesthetics and lettable or living space. Although trench grilles are load-bearing, it is not advisable to place items of furniture over them, as this will affect performance. In terms of commercial offices, the surface area of the grilles could impact on what is deemed lettable space, and this could have a significant impact on the developer's return on investment. Clearly, the narrower the trench, the better. Ultimately, if size of the trench is the main concern, selections may need to be based on forced draft products, giving much higher performance at smaller heights and widths. Most manufacturers will provide a matrix of outputs. Here is a typical matrix for natural convection. This particular matrix is based on given design conditions, in this case 75-65-20, so no correction factor applies. From the matrix, you can see that a unit with a height of 90 mm and a width of 140 mm will provide 190 watts per meter, so it is the ideal selection for the heat requirement of 169 watts per meter. What if the design conditions are different? What if they were much lower, as common with a heat pump or high-efficiency boiler? For example, 55-45-20. By using a correction factor matrix available from most manufacturers, the actual output per meter can be calculated. You can see from the matrix that the correction factor is 0.5. To apply the correction factor in this instance, take the heating requirement of 169 watts per meter and divide it by the correction factor of 0.5, which equals 338 watts per meter. From the matrix, you can see that there are two possibilities. A unit with a height of 90 mm and a width of 340 mm will provide 385 watts per meter, or 192.5 watts per meter at 55-45-20. B, a unit with a height of 110 mm and a width of 260 mm will provide 349 watts per meter, or 174.5 watts per meter at 55-45-20. The final consideration should be that of the finished grille. This is of major importance to the architect and building owner. The selection will need to look great, match the building decor, and of course be practical. Performance outputs are generally based on grilles having open space of 70%. Some decorative grilles have less open space, and this will impact again on the performance of the trench climate convector. As an example, a correction factor of 0.93 needs to be applied when selecting a wooden decorative grille having open space of 52%. If we go back to our example earlier, at the lower design conditions, when you apply the 0.93 correction factor, the corrected output for Unit A is 179 watts per meter, and the correct output for Unit B is 162 watts per meter. Unit A provides an output of 385 watts per meter, or 193 watts per meter at 55-45-20. Unit B provides an output of 349 watts per meter, or 175 watts per meter at 55-45-20. Option B is now below the requirement of 169 watts per meter, and as a consequence should be discounted. Option A is now the preferred selection. Okay, so now we would like to attempt to heat the whole space using trench climate convectors. We'll use the same building layout and design conditions at 75-65-20, a heat loss of 13 kilowatts and 19.5 meters available for active lengths, giving us a requirement of 666 watts per meter. So, let's go back to our matrix and make the selection. A. The obvious selection is a unit with a height of 140 mm and a width of 420 mm, which will provide an output of 792 watts per meter. B. The other option would be the biggest unit, with a height of 190 mm and a width of 420 mm, which will provide an output of 909 watts per meter. Clearly, option A would be the preferred choice at these design conditions, even if correction factors for varying grilles apply. What if the design conditions are different? For example, 55-45-20. The same correction factor of 0.5 would apply, meaning a corrected requirement of 1,332 watts per meter. As you can see from the matrix, this cannot be achieved with a natural convection unit. We therefore need to consider alternative unit types. The obvious alternative is to use a fan-assisted unit. But care must be taken here, as fan-assisted products have different correction factors to natural convectors, as shown in this table. Under these conditions, the correction factor for the fan-assisted product is 0.6, meaning a corrected requirement of 1,110 watts per meter. From this matrix, for fan-assisted trench climate convectors, it can be determined that a unit with a height of 145 mm and a width of 260 mm will provide 1,949 watts per meter, which is then corrected to 1,169 watts per meter at 55-45-20. This meets our 666 watts per meter requirement. Please note, this matrix is based on a medium fan speed, but it's worth checking with your preferred manufacturer beforehand. If you are concerned that the output is too great for your requirement, there's no need to be. Units can be controlled to operate with the fan running on startup, then they can be switched off at a predetermined temperature, leaving the units to operate as a natural convector. If the physical size of the trench climate convectors is still an issue, then consider using forced draft equivalents. Before we start to talk about cooling, some of the questions we often get asked relate to cooling loads, dealing with condensation, and noise levels. So let's go through the basics. What is the difference between sensible, latent, and total cooling? Sensible cooling is the amount of energy required to reduce the temperature of the air in the space. Latent cooling load is a measure of the amount of energy that is necessary to dehumidify the air in a building. Dehumidifying is effectively taking the moisture out of the air. It's normally the humidity that is more uncomfortable for occupants than temperature. Total cooling is sensible plus latent. It's the total calculation that should be used when selecting trench climate convectors for cooling. We will use the same building example. To calculate cooling load, there are many factors to consider. These include heat gains from solar, lighting, electrical equipment, people, and adjacent rooms and floors. In this instance, we've calculated a total cooling load of 24 kilowatts and design conditions of 7, 12, 27. It's assumed that a 4-pipe system is best suited to this application. It is recommended that you split the area into zones and proportion the cooling load accordingly, as illustrated here. Then, analyze the data from your preferred manufacturer, like the example shown. From this, and basing the selection on 8 volts, we select the following. For zones 1, 2, 3 and 4, we can select the unit at 2,800 mm long, giving an output of 5,052 watts per unit. And for zones 4, 5 and 6, we can select the unit at 1,200 mm long, giving an output of 1,739 watts per unit. This will achieve a total cooling output for the entire space of 25.43 kilowatts. At this stage, check that the noise level at 8 volts suits the application. In most cases, once the selection has been made on cooling, it's likely that the heating performance of the selected unit is greater than the requirement. This isn't a problem, as the heating can be selected based on lower fan speeds. For this example, based on the design conditions of 55-45-20, you will note that this is easily achieved at 4 volt speed, providing 14.28 kilowatts. Therefore, this easily covers the 13 kilowatt requirement. All manufacturers will provide cooling and heating outputs according to design conditions at varying speeds on request. We've already talked about latent cooling being the removal of humidity in the air. Condensation occurs when the air in the space is conditioned to reduce the humidity. This is latent cooling. Water is drawn out of the airstream as it passes across the coil. Condensate is collected in the condensate tray fitted below the coil. Removal of the condensate can be by gravity drain or by a pumped system to a discharge or collection point. It's important that condensation rates are calculated to ensure proper drainage. Based on the 2.8 meter unit selected in this example, 3.9 liters an hour of condensate will form. Let's think about noise. We'll now look at sound power, sound pressure, and noise rating. In simple terms, sound power is the cause of the noise, in this instance the fan unit within the trench climate convector. What is sound pressure? If sound power is the cause of the noise, then sound pressure can be considered the effect of the noise. Sound power and sound pressure are normally quantified by the manufacturer. A forced draft climate convector emits the same sound power irrespective of the room in which it is installed. The effect, sound pressure, depends very much on the room itself. Noise ratings, known as NR, serve as a European standard method to measure and specify noise in buildings and occupied spaces. They are commonly used in the measurement of noise from mechanical sources, such as heating, ventilation, and air conditioning systems, so it's important to consider the noise rating in relation to the application. Here are some examples of typical noise ratings for different building types. NR25 is recommended for concert halls, broadcasting and recording studios, and churches. NR30 for private dwellings, hospitals, theatres, cinemas, and conference rooms. NR35 for libraries, museums, courtrooms, schools, hospital operating theatres and wards, flats, hotels, and executive offices. NR40 for halls, corridors, cloakrooms, restaurants, nightclubs, offices, and shops. NR45 for department stores, supermarkets, canteens, and general offices. NR50 for typing pools and offices with business machines. NR60 for light engineering works. And NR70 for foundries and heavy engineering works. The relationship between noise rating and sound pressure is not a constant. It depends on the characteristics of the noise itself. For ordinary intrusive noise found in buildings, such as trench climate convectors, the noise rating would be between 4 and 8 decibels lower than the sound pressure. It is recommended that noise values are calculated for each application. It's often the required noise level that determines the final selection of the trench climate convector. Selections may need to be adjusted to lower fan speeds and voltages to meet the noise requirements. Now we've made our selection, what's the next step? One issue may be the width of the grille and the impact on lettable space. There is always an option. This is an example of a solution offered for a major project in London. The client required high-performance heating and cooling, but was restricted on the width of the grille and the financial impact on lettable space within the commercial office. There was also limited floor depth available. The solution was to produce the equipment with a narrow grille, minimum height, and construction offset, with 50% sitting under the finished floor. Trench climate convectors can be tailored to suit exacting requirements in terms of length, height, and width. They can be enlarged to enable the laying of pipes, cables, and controls. Trench climate convectors look good, but why settle for good when you can make a statement? They can be used to house lighting, creating a low-level dramatic effect to facades. Another way of enhancing the design is to link the convectors together to form a continuous run. You could consider specifying straight or angled dummy units to do this. What about curved facades? Curved trench is always tailored to match the facade exactly, and active elements can be incorporated into the design. It is recommended that you consult with a specialist manufacturer to help you. When designing, it's also important to consider potential installation issues. So, we should think about how the equipment will be installed within the floor, how the units will be fitted and leveled to the finished floor. Most trench climate convectors are supplied with standard height adjusters. Quite often, the floor void can be greater than the standard adjustment, and therefore there may be a requirement for extended height adjusters, or in some cases, specially manufactured supports, as per the example shown. Not only can the physical installation be an issue, but the water connections can also be an issue, so these should be considered in advance. There are generally two ways trench climate convectors can be piped up. The first is in series. This is a cost-effective option, but take caution in your design to ensure a balanced performance across all active units. Alternatively, they can be in parallel. This can be more expensive and time-consuming, but provides optimum heating and cooling performance for each individual active unit. Please consider control functionality before deciding your preferred piping option. Control options are often overlooked, but can be so important. Control options are plentiful, from a simple room thermostat to self-regulating integrated controls to full BMS integration. The control strategy and method needs to take into consideration not just the building, but occupancy, which is often forgotten. From an energy management perspective, The more you can put in at the front end, the better and more efficient the system will run. Our last topic in this session is regulatory compliance, safety, and sustainability, which are all essential factors in the design and specification of any construction-related product. Firstly, it should be noted that trench climate convectors are specifically designed to be installed in the floor, around the perimeter of a room, and if placed elsewhere, performance and occupier comfort would likely be greatly reduced. Application and design must support the creation of buildings and spaces that are accessible and inclusive. When specifying trench climate convectors, approved document L, which covers energy conservation and power, should be followed to meet Building Regulations 2010. This may result in reduced operating temperatures. Building Regulations Part B cover fire safety. It is recommended that delegates take a look at RIBA's recommendations to government in relation to fire safety. Fire safety should always be taken seriously. Trench climate convectors, be they natural, fan-assisted, or forced draft, having low water temperature heat exchangers, should be treated like a radiator when considering fire safety. There is no fire risk with soft furnishings, providing the equipment has been installed in accordance with the manufacturer's instructions by suitably qualified persons. With electric trench climate convectors, there is a risk of obstruction causing overheating, which could lead to a fire. Care must be given to ensure nothing is placed on top of the grill, such as furniture or long curtains, and that grills are narrow enough to prevent items falling through. Thermal cutouts should always be fitted by the manufacturer to prevent overheating. BSEN 16430 is the European standard defining the technical specifications and requirements of fan-assisted radiators, convectors, and trench convectors. The thermal performance standards for trench outlined in BSEN 16430 should be adhered to. This standard also outlines manufacturing requirements that impact health and safety, including factors such as the product should have no sharp edges and should be pressure tested. Therefore, you should always check if the product complies with BSEN 16430 when specifying. Heating, cooling, and ventilation systems must always be fit for purpose, with the building usage and occupants taken into account. So, grill choice should not only be aesthetic, but also be suitable for the application in terms of load bearing and grill spacing. Grills should never cause obstruction when installed in access and egress routes. In construction today, sustainability is crucial. Renewable heat sources should be a primary consideration in building design, and energy-efficient trench climate convectors that are compatible with low-flow temperature systems should be chosen. The life cycle of the trench climate convectors should also be considered, with preference given to recyclability and longer life expectancy. In addition, it is recommended that materials sourced to produce trench climate convectors are both sustainably and ethically sourced. Your chosen manufacturer should be able to provide further guidance in this area. Trench systems generally require minimal maintenance, but in the unlikely event of a breakdown, the top grille should be removable to enable easy access. The grille should be removed periodically, ideally twice a year minimum, and the trench duct and heat exchanger vacuumed, removing any dust and debris. That brings us to the end of our CPD training. Thank you for completing this course. We hope you found it of interest. Please visit jaga.co.uk/CPD feedback, where you'll be asked a few short feedback questions in order to obtain your CPD certificate.